Hello everyone and welcome to PC Retro Tech. Now there was no video last week because I've been working really hard on some new PC assembly language demo effects. So I've done one of those and I'm working on a second which is nearly finished, and I hope to maybe even get a third and make a really epic video about that in about the next week or two. So stay tuned for that, but in the meantime we have some work to do. So you remember on the channel I had this very large collection of video cards that I bought online, and I've been taking selections of about 7 cards at a time and checking them out on my Pentium 3 at 1.45 gigahertz. So we're going to keep doing that this week. I've taken another random 7 cards and they're all AGP. This will be the second last lot of AGP cards. So let's get stuck in and see what we've got. Let's go through the cards, and I have to say when I first saw this lot I saw a Rage 128 and a TNT2 and I thought, yeah, this is going to be a bust. But I was wrong. There's some really fantastic cards in here. So let's start with them in order. So the one here is a very well known card. It's an Asus AGP V7700, and before all the current hoo-ha you could pay €70 for one of these. I noticed they've gone down quite a lot recently. I guess there are fewer people buying this sort of thing online at the moment, and so the prices have dropped. So it's 32 megabytes, and the reason why this is such an interesting card, it's a GeForce 2 with a core speed of 200 and memory 166, but this is a GTS. Now that means that it has twice the stats of the next card down. So in other words, this has 4 pixel pipelines, 8 texture mapping units and 4 render output units instead of half those values. So this was a well-known card for its performance and highly sought after. The next one is an interesting one for me because I've never seen one before. This is a Radeon 9550. Now obviously that's not going to take any records because we have a 9600 already tried in this rig. But this was actually a later card. It was 2004 instead of 2003. It's 8 times AGP, core speed of 250, memory 200, and the render pipeline configuration is 4244. So this is, it's a 256 megabyte card, and I noticed that the bracket is missing here. And in some of the other cards where it's been missing, I've just assumed that was because the card wasn't working and they'd used the bracket on another card. But I found in one case, the reason the bracket was removed was because the card was sold as a low profile card, so it only had a half height bracket. Now I don't think that's what's happening here, so it'll be interesting to see whether that has been removed because it doesn't work. Now the next card is one of the really interesting ones in this collection. This is a Radeon 9600 TX, and that doesn't sound like it could take a record because we've already tried a 9600, as I said. This is in fact from a supermarket computer as well, a Medion brand, which is a German supermarket brand, and it's only 2003. But the TX had much higher stats than the ordinary 9600. So this is going to be really interesting to see how it goes. So its render configuration is 8488, which is a real monster of a card. So the core speed is 297 and the memory is 270, and it's an 8 times AGP card. So I'm going to be really interested to see this one. I think this can take the record on this machine if it works. So the next one here is an NVG2TA. It's a ProLink Pixel View card apparently, and it's a GeForce 2 card, but it's a GeForce 2 Ti, which again means that it has really good specs for its era. Obviously this is a very early card, so we're not going to expect too much from it, but the render pipeline is 4084, which is pretty good actually. So it's only 4 times AGP, core speed of 250, memory of 200. So definitely an interesting card to compare against the standard GeForce 2s that we've already tried. Now up the top here is the Rage 128, and it took me a little bit of sleuthing to figure out exactly what this is. It's actually a Rage 128 GL, and this is a nothing burger. I mean, it's a 2 times AGP, core speed and memory speed of 103, which seems to be a little bit overclocked over some of the other models in this era. and it's either 16 or 32 megabytes. I wasn't even able to determine that without powering it up. And it's 1998 or 99, so I don't think this is going to perform very well. It'll probably be the slowest one in the lineup today. Now, I guess you're looking at that next card there and thinking that's going to be an interesting one. Well, it certainly is. And the reason is this is another GeForce 4 Ti. And we already know that the GeForce 4 Ti that I had before has taken the record on this rig. So this will be fantastic if it works. And the reason I'm really personally excited about this one is that the fan on this one looks intact. Whereas unfortunately on my GeForce 4 Ti, the one that has taken the record, the fan is, well, it was actually removed and replaced with basically glue, with a completely different kind of fan that doesn't really fit. So this could take the record as well. It's obviously going to have similar specs to my other GeForce 4 Ti. So its core speed is 275, memory 275, and the render configuration is 4284, which is again another monster card. So we've got all the really good cards, I think, this week. They're just coming out in random order, but this is really fantastic. I mean, if any of these work, it's going to be fantastic. So the last one here is nothing to talk about. It's the much maligned TNT2 M64, which we've seen before. I don't know if it's 8, 16 or 32 megabytes. The core speed is 128 and the memory speed is 150. It's 4 times AGP. Nothing to talk about really, not one of the interesting cards in the lineup, but we'll benchmark it anyway, just so we have something to compare with. So let's get stuck in and see how the benchmarks come out for all these cards. I am really looking forward to seeing how these go. I haven't even plugged them in to see if they actually work yet. Well, I finished another marathon benchmarking session, and the good news is that all of the cards made it just fine to the desktop, but unfortunately you can see I've had to exclude one of the cards from the benchmarks because it hung during the 3D Mark 99 test. It always hangs at exactly the same point in the 16 megabyte texture test, so I know it's not a random overheating issue, and I suspect that the card itself is actually just faulty. So you can see that 4 of the cards have done quite well here, but the other 2 actually really surprised me and did quite reasonably, given that they're much earlier cards. I'll say a little bit more about that in a moment. Now, as far as records go, we're of course looking at that Radeon 9600 TX and the Asus GeForce 4 Ti to see if they're likely to break the records on this rig. And at least on this benchmark, the Radeon 9600 TX does actually break the record by about 11 points, but as we've seen before, that's not really important because this benchmark only tests the pixel pushing power of the card and some very basic 3D functionality. In fact, the previous record holder was a Riva TNT2, so that should give you an idea of how much stock to place in that. Now, I'll go through the cards individually. The Asus GeForce 2 V7700, that's a really smooth card. It ran the benchmark very, very well, and you're typically getting frame rates up around the 90s. I did notice it was blurry though on the desktop at 640/480, and so I jacked the resolution up to 1024/768, and then it was crystal clear. And I thought this might be a problem with my monitor, but I tried a few other cards, and it seems like all the cards are like this. They have their preferred resolution where everything's really sharp, and everything else is just a little bit off, which surprised me a little bit. So the next card was the Radeon 9550, and unfortunately this had a really badly clacking fan. So this was the one that had the missing backplate, and I think now we know why. It was so loud, in fact I had to put something up against the machine so that my neighbours wouldn't think I was running a jackhammer indoors. So you can see that's done pretty well in this benchmark, and it's a little bit ahead actually of the Radeon 9600 that's taken records on this rig. So that only got 7382 on this benchmark, but again that's not really important. So the Radeon 9600 TX card worked really perfectly, flawlessly in fact, except that it was just very slightly blurry at 1024/768. But I don't think you'd notice that if it was the only card that you had. It was definitely enough that I'm sure, but not enough to really, be disturbing or anything like that. So the next card is the ATI Rage 128 GL, and I was really surprised about this initially until I looked back at some of my other ATI Rage 128 scores and found that it's basically the same. But this is actually, around twice the speed, or more than twice the speed of a Rage Pro Turbo or a Rage XL, so it isn't doing too badly for its era. Remember, this is a 1998-99 card, so we weren't expecting very much from it. The Asus GeForce 4 Ti card is a little bit of an unfortunate story here. It works just fine and I can get a benchmark out of it, but unfortunately there's a lot of green pixels on the textures, artifacts basically, and some purple ones as well. Also, when I plug in just the VGA cable instead of the later style cable, I just get red on the screen, so I don't get any of the other colors. So there are definitely some serious hardware faults in this particular card, and I did all the obvious things like cleaning the contacts and so on. So I'll be a little bit annoyed if this turns out to be faster than my other GeForce 4 Ti. Fortunately, it's only 1 point ahead on the 3D Mark 99 benchmark, so that's really nothing to worry about. But if it's faster in the other benchmarks, that's going to be a little bit annoying. The ELSA TNT2 M64 at the end, again I was really surprised about this, and this time I had reason to be because I've timed TNT2 M64s before and they only get 4,800 on this benchmark, so this is doing really well actually. Of course I expect it to do quite poorly in the later benchmarks, which we'll see shortly. So let's move on now to the 3D Mark 2000 benchmarks. Well, here are the 3D Mark 2000 benchmarks, and you can see that there's a really nice delineation in the performance here, and the two that are coming out on top are the ones we expected, the Radeon 9600 TX and that artifacty GeForce 4 Ti card. So the question is, has it broken the record in this benchmark? And yeah, both of them actually. So it's a little bit disappointing that the GeForce 4 Ti is actually faster than my old GeForce 4 Ti, which was a 4200. So that was only getting 9871, which was the previous record, and now you can see 9997. So it is disappointing that it is artifacting, although it's not a huge difference, admittedly. But the winner so far, and a new record, which let's hope it holds in the 2001 benchmark, is the Radeon 9600 TX card. So at this point, it's looking like we're in good shape to have a new record on this rig. So I'm really looking forward to the third lot of benchmarks. Now, of course, you can see the ATI Rage 128 and the ELSA TNT2 M64 have now fallen way behind. And of course we expect this, they're much earlier cards. That Asus GeForce 2 though is still performing remarkably well. That's a GeForce 2, not a GeForce 4, and that GTS really makes a difference. As I said, that doubles the stats on all the render components, and so yeah, you really got very good performance for years after it was made. And it held its own against much later cards. So I think people would have been really happy to have had that back in the day. And given how cheap they are now, second hand, and how many there are available, there's probably a good time to buy them as well. I certainly wouldn't sell one at the moment, given that they usually go for much more than what they're available for at the moment. So the question is, can that Radeon 9600 TX keep its lead in the 3D Mark 2001 benchmark? So let's take a look at those. And here we have the 3D Mark 2001 benchmarks, and I know you're dying to know whether that Radeon 9600 TX has finally broken the record on this rig. But let me talk about the other cards first. So that Asus GeForce 2 V7700, it has fallen behind here, but it is only a GeForce 2. So for that era, it's doing amazingly well, and that's really because of that GTS that, as I said, almost doubles the stats in the render components. And I have to say that the frame rates in this were really good. So in all three of the benchmarks, it rarely dropped below 30 frames per second, and typically you're getting 75 to 90 frames per second in the games. So this is a really great card, and there's not really any reason I can think of that you wouldn't get one of these at the moment, given how cheap they are, how available they are, and you know, how good they are. Now, of course, in the later era you had this 9550, and if I compare that to a 9600, well, I'm not sure you'd actually notice the difference. There wasn't a huge difference between the scores here. So that's a really nice card, and I didn't have any other problems with it other than that clacking fan, which of course could be replaced or maybe even repaired. It's not entirely clear. Now, of course, the ATO Rage 128 and the Elsa TNT2 M64 look very bad here. But they're very, very early 3D cards, so it's not unexpected. What is a little bit unexpected is that they actually even ran this benchmark. A Rage Pro Turbo and a Rage XL that we looked at before just bombed out in this benchmark. Of course, there were many tests that they couldn't run because they didn't have the necessary 3D hardware. But it's cool that they got through, and I think you'd be pleased if you were buying games in this era that your cards kept going. But you know, performance-wise, obviously, they weren't really very impressive. Now, that Asus GeForce 4 Ti is a little bit of a sad story. That is actually a slightly higher score than my older GeForce 4 Ti. So it would have been nice if that had been the one that had been faulty rather than this one, since it's a faster card. But in a way, I'm looking at it a little bit differently. So I paid about €2 for this card, and actually about the same for the other one as well. And you know, all I needed on that other one was a decent fan. The fan that was on it was just hot glued on, and it looked really ugly. It wasn't even sitting properly into the heatsink. So it's nice that I can take the fan off this, and I've done that now, put it onto the older card, and now I have a complete card that's working. It just would have been nice if it had been the other way around. But anyway, clearly the Radeon 9600 TX is the star of the show, and it's substantially ahead of the GeForce 4 Ti. And I can tell you that in fact it did even beat the 9600. So the 9600 got a score of 75.25, which was actually the record for this rig on this benchmark for me. So at 84.06 you would definitely notice that. It was only 200 points ahead, remember, on the 3D Mark 2000 benchmark, so not very much at all. But here it really shines, and so now I have finally found a new record holder for my rig, and I will actually use this card as the main card for this rig now, since I had absolutely no problems with it whatsoever. Even the fan is silent. The only minor niggle I had was, as I said, the 1024-768 was just slightly blurry, which I'm sure is a feature of the card rather than the monitor. But it's not anything that you would notice unless you were comparing it with something else. So I'm very, very happy. This has been a great success. We still have one lot of AGP cards to go next time, and I have no idea what's in there. I really haven't looked. So I don't know whether we could even beat this 9600 TX. Let's wait and find out. Anyway, to finish off today, I thought that I might go through some details on why AGP was better than PCI. Now, of course, it's obvious it had higher bandwidth, etc. But why was that? What are the technical details? So stay with me, and I'm going to go through some of the features of AGP and why it was such an improvement. In order to explain how peripherals connected to an ISA slot actually work, I've drawn this little block diagram, and I apologize that it's in pen, but the NVIDIA drivers are stopping my tablet from rendering videos at the moment. So the basic concept is that you have a CPU that's connected to the rest of the system, to everything else, via something called a bus, which is a series of lines that can carry addresses and data. So you want to address two main things in the system: memory devices and I/O devices. So memory devices would include things like your system RAM or RAM on board peripherals. For example, a CGA card has memory on board. ROM chips, which could also be on cards, or maybe the BIOS in the system. And the I/O devices include things like control registers, for example, a palette register on a video card. Now, the basic way they work is the same in both cases. You have an address, either a memory address or an I/O address, and you then read or write to them. So there are some extra pins here which select between memory or I/O, between 8 or 16-bit transfers, and between reading and writing. So in the 8086 you have 20 pins for the actual bus itself, and you need 20 because there's a megabyte of address space in those machines, and 20 bits gives you addresses for a megabyte. Now, there are actually only 16 of these pins were used for I/O devices, and actually in early PCs they only used 10 of those pins, so there are only 1,024 separate I/O addresses. Now, the 8086 had 20 pins for addressing, and 16 of them were used for data transfer, and 8 of them were used for 8-bit transfers. And the 8088 could only do 8-bit transfers, so it only had 8 pins for data transfer. But they used the same pins for the addresses and for the data that was being read or written from those addresses. Now, that was a bit of a problem because it meant that you couldn't do memory accesses, for example, in a single cycle. So the CPU was running at a clock at 4.77 megahertz in the original PC, and in fact the system RAM that was used at the time was 200 nanoseconds, which could actually access in a single CPU cycle. Because you couldn't put the address and the data on the lines at the same time, they had to break it down. So there are actually 4 cycles per bus access. T1 was where the address was put on the lines, and T2 through T4 is where they would switch to data mode, wait for the data transfer to happen, and then reset everything to go back for the next bus cycle. And various things like CGA card, for example, could add additional wait states to this if it couldn't keep up, and so it could even take 20 or 30 cycles for addressing memory in a CGA card. Now, the 8088, as I said, only has 8 data lines. Now, that might seem like a big restriction. You might wonder why they did it, especially since the 8086 came first. But when it came out, there were very few 16-bit support chips and peripherals available, but there was a huge ecosystem of 8-bit stuff. So it made sense to be able to leverage all of this, and it made for some very cheap computers at the time. And also you've only got 8 lines instead of 16 running everywhere, which means cheaper motherboards. Now, you can connect directly to peripherals, but that's only in very, very simple computers, and they do that in something called minimum mode. But the original PC didn't use minimum mode, it used maximum mode, which meant that there was an additional bus controller chip, and it mediated between the CPU and everything else. So all of these lines were just connected directly to that chip, including the control lines, and then this was connected to everything else in the system on the bus. Now, it also had some other functions. For example, if you were doing an unaligned memory access on a 16-bit machine, then it would have to break it down into 2 accesses, and so that was one of the functions that it had. And there was also an address and a data buffer in this chip as well. Now, the 8088 had to break everything down into 8-bit accesses, and so it had special circuitry internally for doing that and took over at least part of the function of this. This is the basic structure of how everything works. Now, all of those lines are available on the ISA slot. You have 8 bits of data here, and the 16-bit part of the slot you have a further 8 bits of data, and all the address bits are there. They don't use the same pins for address and data like the CPU. They're kept separate. And then there are IRQ lines. So a device like a hard drive controller might send a pulse down a given IRQ line that corresponds to that controller, and tell the CPU to run a special handler routine, which would be in a ROM or in maybe in the operating system or even in user code, that would handle that request. So that's called an interrupt, because it interrupts whatever the CPU was doing to get something else done. And so the other thing that was necessary was DMA access. So instead of doing everything byte by byte via the CPU, you could do it directly with memory using a direct memory access controller. And so there were pins for DMA access in the ISA slots. The other thing is that the 16-bit ISA controller had bus mastering, which meant that peripherals could actually take over the bus themselves. And even some early hard drive controllers had 8186 CPUs in the controller, and so they were quite sophisticated. So bus mastering enabled the peripheral to basically take over. So those are the basic details about ISA. I'm not going to do PCI and Visa Local Bus in this video. Instead, I'm going to jump now directly to AGP. From the point of view of most PCs, PCI and AGP were 32-bit standards, and so they had 32 address or data lines. And in fact, AGP was just really an extension of the PCI standard. It was based on it and just a superset. So it tried to deal with some problems that PCI had. So PCI was great in one way, that you could have a lot of cards in the system that wouldn't interfere with one another. When you start up the system, the bus arbiter would use software to set the addresses of all of the memory blocks in those PCI cards and the I/O addresses. So they were all software defined, which means that they didn't have to conflict with one another and weren't hard-coded. But it meant that you had to have some kind of protocol for accessing those addresses. So basically these were called frames, and you would send an address frame to specify where you wanted to address, followed by some frames of data. Now, the cheaper PCI cards were just address data, address data, address data, and they didn't have a burst mode. But the burst mode did allow you to transmit a certain amount of data all in one go. Now, the problem is that some other PCI card might want to be using the bus at that time, and this would mean that you had to stop all the time and check whether there's anything else needing to use the bus, and if not, request the bus again and do the next lot of data. But this meant that there was a lot of overhead in accessing the PCI bus. So AGP solved this by having a dedicated port just for graphics. So it's like a separate PCI bus in a sense. But because it was dedicated, it didn't have to worry about anything else being on there. There was only the AGP card. And in addition, you could actually run it at a higher frequency because it was separated from the rest of the PCI bus system. Now, there were a couple of other theoretical advantages here. They used something called sideband addressing, and they were also able to split up address requests from their corresponding data frames. So the sideband addressing allowed you to continue doing AGP requests independently of data on the 32-bit address data lines. So there was a sort of sideband in which you could send additional AGP requests while a long data request was being handled. So you might be loading a texture, but at the same time along the extra 8-bit sideband, you're sending additional AGP requests. So they were more technical improvements, but the other main improvement was the GART. So this is a graphics address remapping table, and it basically is exactly what it sounds like. In the graphics card, there is a set of addresses that are set up for holding textures or whatever, but the reality is that these memory locations might be scattered all over the place, and the graphics address remapping table maps that orderly set of addresses to wherever they actually are stored in memory. And this means that you could even use system RAM to store textures. So it didn't even have to be addresses in the AGP card itself. And what that means is that you didn't need to load the texture from hard disk into system RAM and then from system RAM into the graphics card before it could be used. You could work with it directly in system RAM if that proved to be more efficient. Of course, in the end, this led to cards that just use system RAM instead of having more expensive graphics RAM, and of course there were a lot of very cheap solutions that used this as well. But I'm sure you've seen GART drivers for AGP cards, and this is what that's for. So those are the main improvements of AGP over what came before, and that's basically all I have time for today. So I hope that you had an enjoyable look at these graphics cards from the collection that I purchased, and hope that you enjoyed this look at how AGP gets around some of the limitations of having graphics on shared buses. So thanks very much for watching, and hopefully you enjoyed this video. If you did, don't forget to like and subscribe, and we'll see you in a later video. Bye.